6 rational exponents. This is all about dealing with expressions where the power is a rational exponent, the rational number, like 4/5. Now, actually, we kind of know how to do it already. We've been doing it in past couple problems, lessons. Remember when I gave x10, the cube root of x10? We just wrote it as x10 divided by 3. And that's how it works. If I give you something like a cube root of x, you could write that as x to the, there's a power there, 1, power over root, 1 over 3. Alright, so in general, if you have a k root, x to the m, you write it x to the m over k. Right? Power over root. That's the key. Power over root. Power over root. So that's the whole idea. That's how we write it. So all I want you to do here is rewrite it. In this case, I want you to rewrite it. So 10 to the 1/4, remember this is the power, this is the root. So we're going to write it as the 4th root of 10 to the 1st, or just the 4th root of 10. Same thing here, power root, the 5th root of x to the 3rd. We're going to rewrite this one. So 15, power is 1, so 1 over 3. Same thing here, 7 to the 1/4, x to the 6/4, and y to the 9/4. You could reduce that if you want, but that's the general idea. It's how to rewrite it. Now let's evaluate some expressions. So this first one, remember what a negative power does. Negative power flips it. Now it doesn't flip the rational, it flips the base. So it's going to be, and again we're talking about the negative here, it's going to be 1 over negative 3.125, so 1/5. Right, so negative power flips the base. Now from here you got to figure out what's the 5th root of 3.125. Now again, it's not one to say to memorize, but think about it logically. What thing gives you a 5 at the end? Probably kind of works. It's 5. So 1 over negative 5 will be the answer there. Okay, now we get this one, 256 to 3/8. So you can rewrite that as 256, 8th root of 256 to the 3rd. But really the way you want to do this is like this. When it's like that, I want you to solve it. I want you to do the root first. That's the trick. Root first. So when you get a problem like that where you have a number to a fractional power and you want to simplify by hand, do the root first. So we're going to write like this. The 8th root of 256, then we're going to get to the 3rd power. 8th root of 256, again, not one I had to memorize, but you can think about it logically. Probably figure it out. It's 2, and then 2 to the 3rd is 8. So again, we do the root first. So same thing here. Right? 2/3, we're going to do the root first. So we're going to do the cube root of 125, and then we're going to square it. Cube root of 125 is just 5. 5 squared is 25. Same as the next one. I'm just without showing work. 4 to 3/2, right? So we're going to square root first. Square root of 4 is 2. 2 cubed is 8. So it's 24 over 8, which is 3. So that's how you do those problems. You always do the root first. If I gave you something like 27 to the 2/3, you'd be like, okay, cube root of 27. We're going to square that answer. Cube root of 27 is 3. 3 squared is 9. So that's how you do those. Now let's talk about simplifying expressions. So look at this first one here. Now I'm going to do an equivalent problem first. Let's say I gave you p squared times p cubed. Be like, oh, you just add the powers. P to the 5th. 2 plus 3. Same thing here. I don't care if it's rational exponent, you do the exact same thing. 1/4, oh, the same base, plus add the powers. 9 over 4. So in this case I get p to the 10 over 4, also known as p to the 5/2. This one, now I put this here on purpose. That's what the book does. The book is crazy. Sometimes. A lot of times the book's good, sometimes the book's kind of crazy. So what's going on here is this. I want you to go, okay, I don't want a negative exponent, so we flip it. So this will be 1 over r to the 4/5. Done. That's all I want you to do. The book sees this and goes, oh, you have to rationalize this. So they multiply both top and bottom by r to the 1/5. Right, because we want this to be 1, so that's what they do. I don't know why I put the square root there. The book's crazy. That's all I want. And I actually prefer that, but whatever. That's what I want. Same thing here. I gotta say same base, I gotta add the powers. A to the 3/4 plus 1/2. Oh, you gotta add a common denominator. You gotta add fractions. And then when you add fractions, all you do is find a common denominator. In this case, it's 4, so a to the 3/4 plus multiply by 2/4, and you get a to the 5/4. Right, just adding fractions like normal, good old days. Here, again, just pretend it's like this. How do we do that? We subtract the powers. So same thing here, top over bottom, subtract the powers. X to the 3/5. That's how you simplify rational expressions. Keep in mind the things we talked before, right? We generally want no. If I say you simplify, I want no negative expressions. No expressions that have. Make sure it's not a complex fraction. Okay, no, I'm fine with complex fractions. No, it has no exponents that are not positive integers in the denominator. Yeah, that's fine. Except for any remainder. Yeah, that's true. So this, I don't care about complex. We like complex fractions. What are you talking about? Okay, so a couple things here. This one, I want to point out that you cannot just divide them, right? These are different these are different roots. Like if we rewrote it, it'd be 32 to the 1/4 over 2 to the 1/3. So you can't simplify because the powers are different. So with here, everybody can't do much. What you can do, we're going to get into this later, is you could rewrite 32. This is a little preview to next chapter. We're going to do this a lot more next chapter than we are going to do this chapter. We're not really going to focus on this chapter. What you could do is you could rewrite this at the same base. 32, the same thing as saying 2 to the 5th. So you have 2 to the 5th to the 1/4 over 2 to the 1/3. And then if we have that, that's the same thing as saying 2 to the 5/4 over 2 to the 1/3. So again, what I looked at it do, I was like, wait, I can't do anything here. They're the same, different powers, they're not the same base, I can't do anything. But what I did is we wrote 32. I was like, wait, I could rewrite that. 32 is the same thing as saying 2 to the 5th power. So I switched 32 with 2 to the 5th, and I simplified it a bit. Again, we're going to do this a lot more next chapter. It's like a little preview. We're going to do this a lot more next chapter. And now you go, wait, these are the same base. Remember how we do with the same base? Same thing we did up here. When you have the same base, you just subtract the powers. So my next step here would be 2 to the 5/4 minus 1/3. Then all you have to do is find the common denominator. So it'll be like 3 and 3 and 4 and 4. Right? Subtract the powers, so you get 5 over 12. 3 and 3, so 15 over 12 minus 4 and 4. Common denominator, 4 over 12. So you get 2 to 11/12. That's how the problem's done. Again, we're going to do this way more next chapter, and we're not going to do this chapter. Just a little preview. But that's going to be we're going to do a lot next chapter. Just get the rewrite things so the bases match. That's a big part of next chapter. Anyway, this next one, let's do the same thing here. Let's rewrite the base here. So again, all this is like this will preview to next chapter. Get you going. So 16, can I write that as a different way? Any powers that go to 16? There's a couple. I can write that as 4 squared or 2 cubed. Let's go with the 2 to the 4th, sorry. Let's go with the 2 to the 4th one. So we're going to have the cube root of 2 to the 4th x to the 4th. Remember the way we do this? You divide the powers, right? So 4 divided by 2 is 2. Wait, let's write right here. 4 divided by 3, sorry, is 1 remainder 1. So I have 1, 2 on the outside, 1, 2 on the inside. Same thing with x to the 4th. 4 divided by 3 is 1 remainder 1. So 1x on the outside, 1x on the inside. That's what they want for that one. Again, all this is kind of a preview to next chapter. Let's rewrite this one. 9, the same thing as 3 squared, g squared. All to the 1/4 power, or 4th root. So we're going to multiply it out. We get 3 to the 1/2, g to the 1/2. Or if we want, square root of g, 3 and g. Either way is fine. This one's a little different. Because notice how they have the same power, the same root. So I could actually divide these. I could get 5th root of 64 over 4, which is 16. Like, okay, done. But again, all this is a preview to the next chapter. So once you get, this is all about practice. How can I rewrite 16? Write that as 2 to the 4th. So the same thing as saying 5th root of 2 to the 4th. The same thing as saying 2 to the 4/5. Again, you won't get any of this on the quiz or test, but You can see this a lot next chapter. A lot next chapter. So there's a little preview for next chapter. Anyway, let's move on. No, not that one. Last one. A population of 100 deer is reintroduced into a wildlife preserve. Suppose the population does extremely well and the deer population doubles in 2 years. Then the number of deer, D, after T years is given by its formula. So again, we have a formula. Make sure you know what each thing stands for. T is years, D is number of deer. So we have that formula. How many deer will there be after 4.5 years? So that's our T. So all I gotta do for A is plug that in. So I can plug 4.5 over 2. Again, it's an application problem, so feel free to use your calculator. I want you to use it. I'm going to do that by hand. So it's going to be 100 times 2 to the 4.5 divided by 2. So about, why did I have that 100? Okay. So let's do this. I didn't realize they had answer divided by in front. Delete, delete. Okay, there we go. 475. Actually, I think 476 if we round. About 476 deer. B, make a table that charts the population of deer every year for the next 5 years. So we can do it for every year. We can plug in 5. I'm not going to do that. Make a graph using the table. So, again, I'm going to just use a calculator. Let's graph in our calculator. 100 times 2 to the... Now remember, we don't have T, we just use X. I could graph it. If they want a table, I could look at my table too. So every 5 years, let's go down here. So 0, 5, 0, 5, 6. Actually, let's show you this. You could change the table values if you want. If you go to window, if you go to table set right here, it lets you go, where do you want to start? We want to start at 0. What do you want to count by? So I'm going to ask by 1s, I'm going to go to 5. Now if I go back to my table, it's counting by 5s. So you see how huge it gets. I'm going to go back and put it back to 1 because that's a standard, industry standard. But this will show you can change your table values. Anyway, let's go to my graph. Let's make it standard, so zoom standard. And I can barely see it. Might want to zoom fit this one. There we go, zoom fit. See if that gives me a better picture. There we go. It's basically saying it's going like that. And you can already see at the very beginning because remember it crosses at 100. That was the initial amount of deer was 100. That's why we couldn't really see it. So this is C. We did be online. Using your table in the graph, decide whether this is a reasonable trend over the long term. So again, anytime I say this, over the long term, most times it'll be no and no, right? Eventually it'll be the planet of the deer. It'll be so many deer. So yeah, it's not a reasonable event. It's not going to continue. At some point, it has to stabilize. So no, cities will be overrun by deer. There wouldn't be enough deer for the planets. Anyway, that's the lesson.